So good morning, everyone. It's my pleasure to stand here. In the next 20 minutes, I will try to convince you that we can use a lock-free method to resolve conflicts when we do collaboration in cloud storage system. So how do you collaborate with the others? The email is not efficient because you cannot work concurrently. The online editor like Google Doc or Leaf, the functionality provided there is limited. The version control system, they're difficult to use and not user-friendly. But as an alternative approach, you can use cloud storage system to do online collaboration. Because cloud storage system has evolved its functionality from uploading a single file to do online collaboration. But as we know that collaboration will inevitably introduce conflicts. Instead of letting users to learn complex diff and merge instruction, all current cloud storage systems use their own mechanism to resolve conflicts transparently. But unfortunately, their methods do not work well in practice. We started 8 widely used cloud storage systems, including Dropbox, Google Drive, C-File, and NotStore. And our result revealed a series of unexpected and weird behavior, like conflicts despite coordination, and losing updates, and excessively long synchro duration. And you might block collaborator by just opening a file. So to better understand why this problem happens, we did a systematic measurement study. First of all, we collect 10 real-world collaboration traces. 7 of them are provided by users who are writing docs or codes collaboratively using different cloud storage systems. And the other 3 are extracted from the open source GitHub projects. And we replace the collaboration trace by using AWS virtual machine and instructing the machine to upload different versions of the file to the cloud. And we also try to capture all IP-level synchronization transmission with Wireshark. And we find that all network transmission in the cloud are encrypted with HTTP session. So that's why we try to crack the HTTP session by conducting man-in-the-middle attack. And we succeeded with some of them. For those we failed, we just read the official documents and user manuals. And we also read the source code of C-file. By doing this, we have a basic understanding about this principal design, like whether or not they are using full file synchronization or delta synchronization, and their logs and message queues, things like that. So we listed our major findings here. First of all, we find that sometimes the synchronization delay might be very long, might up to hours. So this long-tail synchronization delay might break sometimes will break the time order among file uploads, which will lead to conflicts. The second thing is that we find 5 of the cloud storage systems never use any form of lock. And users who are using these products will easily have conflicts. And for Box, C-File, and NotStore, they are using coarse-grained file-level lock. But as you know, that cloud storage system cannot observe users' real-time editing behavior, so it's quite hard to determine when to request and when to release the lock. So if you lock too early, you will block other collaborators. If you lock too late, your update will be override by others. So you can see no lock will lead to conflicts. And the coarse-grained file-level lock will hardly prevent conflicts. And also, they noticed the problem and tried to resolve the conflicts with 3 different strategies, but none of them are satisfying. So Google Drive only keeps the latest version and discards old version, and user can hardly recover the old version. And the remaining service, you either keep all the conflicting version or asking user to choose among multiple conflicting versions, which leave all burden to the user, which is not ideal. And we also find that So their file level solution is too cost-greedy for conflicting resolution because the majority of the conflicts are false conflicts, which means collaborators are acting on different parts of the same file. So we try to explore the possibility to develop a lock-free collaborative resolution by inferring fine-grained user intention. That's our key idea. So first of all, we will try to infer the operation sequence of the uploaded new version using edit graph. And then if we have multiple conflicting versions, we will transform and merging the operation sequence with minimal conflict. And finally, we just execute the merge operation sequence to the base version. So our first step. So the input is the base version and the uploaded new version. The output should be the operation sequence. Normally, we use the we need to calculate the longest common subsequence using dynamic programming. And then we compare the LCS, the longest common sequence, with the base version and the new version to generate the sequence of delete and insert. But the problem is that the complexity of this algorithm is O(n) squared. And it's too expensive for the cloud storage system because we sometimes need 30 seconds to handle the text file. But as you know, we only need several seconds to upload a file. So it's too time consuming. So our optimization is that we leverage on an edit graph based approach. You can see these fingers that about how to use the edit graph to compute the longest common sequence between two words, properly and purple. The horizontal and vertical edge is given weight 1, and the diagonal edge is given weight 0. So the task of computing the LCS is converted to finding the minimal cost path that goes through the start point to the end point. And using this algorithm, our complexity can reduce to ND. And in practice, D is much, much smaller than the N. And our result shows that we can achieve 150 times speed up. So let's come to our second step. If we have conflicts, first we need to detect whether or not we have true conflicts. To do this, we just generate the operation sequence S1 and S2 for two conflicting versions, and we try to merge them together into a temporal sequence and sort it by the operation position. And then we check whether or not any position is conflict with the one behind it, just check their impact range. If we are lucky enough, we only have false conflicts, then we can just apply this merge sequence to our base version to generate the new version. But if we have true conflicts, in this case, it's impossible to correctly resolve conflicts. But our principle is that we prioritize mitigation, the user invention, and while preserve the potentially useful information as much as possible. So we classify different true conflicts and use different strategy to resolve them. We have only 3 kinds of true conflicts. Note that we don't have insert and delete conflicts. Oh, I have to mention that the less than symbol means that the first operation's position is less than the second operation. For the delete conflicts, we just delete the characters both users want to delete and preserve the other characters with relative information. The example shows here. And for delete and insert conflicts, we notice that the characters to be deleted might be the literal context of the information to be inserted by another person. So it will be quite confusing if we just delete the characters. So what we do is we keep all the information to help user to resolve them manually. And for insert conflicts, we just insert all of them. Okay, then we generate the final consequence, and then we can apply them directly to the base version. But if we have multiple conflicting versions, it's pretty much the same way. We just generate the operation sequence for each version and merge them one by one, and then execute them on the base version. I have to mention that it's not quite often to have multiple conflicting versions. We find only 9% of the multiple conflicting versions, that is large or equal than 3 conflicting versions. So here is our implementation and the evaluation. We built a prototype user-friendly collaborative cloud based on the Amazon's AWS. And then we evaluate our proto system in multiple aspects. The first metric we evaluate is the ratio of conflicts resolved. You can see that we resolved all of the false conflicts and only leave the true conflicts. So our reduction is we reduced 98% of the conflicts. And we also measure the overhand introduced by our conflicting resolution. Our algorithm consists of 2 steps, the operation inference and the operation transformation. They are both linear to the size of the file size and number of operation. And we also measure the total overhand of the conflict resolution. It's only 2% of the time in delivering an upload, which is acceptable. Normally, it's 10 milliseconds to 80 milliseconds. The last thing we measure is the network traffic. When there is no true conflicts, our traffic is almost the same as the NAT store, which combine the full file transmission, full file synchronization, and delta synchronization. But when we have true conflicts, our system have advantages because we only use delta synchronization for both conflicting versions, while the NAT store will use full file synchronization for the conflicting version. So that's why we will have less synchro time. And in summary, given the situations that collaboration has become a major use in the cloud storage system, the current mechanism is not efficient and sometimes very frustrating to user. So we develop a systematic study to understand why this behavior happens and design our lock-free, fine-grained collaboration conflict resolution. And our results show that we can reduce 98% of the conflicts and also keep the transparency. Okay, that's all. Any questions, statements, and concerns?
So we have time for lots of questions.
Okay.
So Jeff Kenning, Harvey College. I think you said you saw a 4% conflict rate in the data you studied, and that's actually very high compared to a lot of other studies. And I'm wondering, do you have insight into why the conflict rate is 4% rather than 1% or 0.5%?
Wait. I said we can resolve almost 98% of the conflicts. Where does the 4% come from?
I may be misremembering, but I thought you said before you resolved the conflicts, there were like 4% of conflicts.
No, I mean that.
Yeah, down at the lower left there, you say the conflict rate is 4%, and a lot of them are false conflicts. So I guess when you say 4% conflict rate, are you saying just that a conflict is any time 2 people update the same file?
Yes, this is about the true conflicts, and we can resolve all the false conflicts and some of the true conflicts. So that's why we can achieve 98% of the conflict resolution. And the other cloud storage system can never choose any of it. They cannot resolve the false conflicts and not true conflicts.
Okay, thank you.
Does that answer your question?
Yes.
Okay, cool.
In am I correct in understanding the intentions that you studied were inserts and deletes?
Yes.
Do you think it's applicable to sort of broader document merging, for example, code or the Photoshop's file format or something like that? Or is that too complicated for this method?
You mean that can we apply this method to a wider range of other files?
Yeah, a wider range of intentions, I guess I'd say.
It should be okay to apply this method to both the alternate file and also the binary file. I think that's fine.
So I think with that, let's thank
Okay.
Hongyi again.
Cool. We're done.